learn. No. Y'all ready? Anthony, could you hit the door? Behind you, thank you. So the test in this unit on electrostatics, primarily we broke it up into what can I do with point spherical circular charges and what can I do with plates. And in particular, you can, I'm going to focus mostly on the written. There might be a couple of curveballs on the multiple choice, but if you work through the ultimate review, you're going to be fine. What can I ask you with point charges? Well, certainly to begin with, I could say, find, wow, why is that so small, Mr. Dueck? Well, let's make it larger. I could say find the force, magnitude, and direction. You know what? That's almost too easy. Now, I would have no problem giving you the force. Remember, we would use F equals K Q1 Q2 over R squared. I have no problem giving you the force and saying find either charge 1 or charge 2 or R. K is 9 times 10 to the 9th. Oh, also, as usual, you can write this down if you want to, or I can print this up if you stick around till the end. Blah. Too easy. Instead, you know what? Almost certainly I'm going to say so where is X? How about let's put location X right there, where this is 0.6 meters. Okay. Asking you to find the electric field at location X. Totally fair game. How would I do that? We had this fancy thing that we called the principle of superposition, which meant you only do one at a time. First of all, for electric field, it's point charges, so I'm going to use, what am I going to use for electric field? By the way, you may want your formula sheet out in front of you, because the biggest issue we found in this was using which equation when? K Q over R squared. So if I'm going to find the electric field at location X, can I move this? Get this all on one page. There we go. It's going to be find the electric field from charge 1, magnitude and direction. That's going to be 9 times 10 to the 9th. Get your calculators out so you can kind of crunch these quickly. This is in coulombs, not in microcoulombs, so they've already done the 10 to the negative 6. All over 0.6 squared. What will the magnitude of the electric field there be? Is that right? 200,000? Wow, those are nice numbers. Newtons per coulomb. Direction. Again, how do I figure out the direction? It's cover up this charge, ignore it. Which way would a positive want to move at location X if it could because of charge 1? By the way, I should say, let's call this Q1. Let's call this Q2. Because like repel. Okay. Then I would find the electric field from charge 2, which is going to be 9 times 10 to the 9th. Charge 2, it's negative 10 to the negative 6. Am I going to put the negative in here? No. Negative 6 times 10 to the negative 6. 6 all over, and it looks like its distance, well, if that's 0.6 and the whole thing is 1.4 squared, no way this will work out evenly. 9 times 10 to the 9th, 6 times 10 to the negative 6 divided by 1.4 squared. And I get 227,500, 27,500. 200,000 was right before? Yeah, okay. Is this right? Someone double check me. Yeah? 27,550. Direction. Which way would a positive want to move if it could because of charge 2? Yeah, also to the right. So my net electric field it's going to be 200,000 to the right plus 27,550. It's not going to be winner minus loser. It's winner plus winner. $228,000, I guess, if I go to 3 sig figs. Newtons per coulomb to the right. What else could I do with point charges? Same picture? Give you a different location just for practice. You know what? How about exactly halfway between? So that's 1 meter, and that's 1 meter. And I could say, find the potential. Okay. So potential, I go or do I? Where would that be right? If I had said find what? Potential energy. Okay? I may do both on your test, probably not in the same question. So that would be wrong. What's another word, the word I prefer, for potential? So it's going to be voltage from charge 1. Remember, I use the wings on the capital V so you don't get this mixed up with velocity. That's going to be 9 times 10 to the 9th, 8 times 10 to the negative 6, all over 1 squared, Carly, or not? No. And you know what? I'm going to argue dividing by 1. Everybody here can probably divide by 1 successfully in their head, even if it was squared, which it's not. It's going to be 9 times 8, 72. 10 to the 9th times 10 to the negative 6 is 10 to the 3rd. So it's going to be 72 times 10 to the 3rd, 7.2 times 10 to the 4th volts. I hope that's right. Someone want to double check me? 72,000 volts? Yeah. Yep. Then I'll find the voltage from charge 2, which is going to be 9 times 10 to the 9th. Do I want the negative here or not? Zach, did you figure it out? What was your question? Because if you had a question, it was probably a good question. No? You sure? I'd really not, believe me. I'm glad you think that I might worry about you, but no. Hey, 6 times 10 to negative 6 or negative 6? Which one? How do I know? So the rule is for forces and fields, forget the sign. In fact, we said this, forces and fields, first line on your formula sheet, forget the signs. We decide the direction for the vectors. How? Like, unlike, or for electric field, which way would a positive charge want to move? It could. For scalars, we put the signs in, and the two scalars in this unit are potential and potential energy. Voltage and potential energy. So it's going to be negative 6 times 10 to the negative 6 all over 1. Squared, Carly? No. In fact, you're going to get negative 54 times 10 to the 3. You're going to get negative 54,000 volts. So the total voltage is going to be 72,000 plus negative 54,000. And we call that, add it up, 18,000 volts? Okay. Now, what else? We called the change in potential or voltage the potential difference. Because what's change in anything? Final minus initial. And what's difference a word for mathematically in terms of operations? Subtract. Okay, so you may see them talk about potential difference. They're really talking about the change in voltage, and change in voltage has appeared all over the place in our equations. What else could we do? Oh, same diagram. Suppose, let's label these charge 1, charge 2. Suppose Q1 is fixed and Q2 is heading east at 5.2 times 10 to the 7th meters per second. Hey, there we go. How far until it stops? Which way does charge 2 want to travel? Want to fall? Want to move? Like, repel, unlike? So charge 2 has a force on it acting to the left, but it's got enough speed right now, somehow, that it's moving to the right. This is sort of like throwing something up in the air. Eventually it's going to come to a stop. When? Why? Do I have a change in height? If I turn my head sideways, I do. Do I have a change in speed? Yeah. Do I have a changing force? Yeah. You know what this is a job for? Are any of these 0? Sadly, only that one. If we were starting out at infinity or ending out at infinity, one of my potential energies would be 0, but sadly, it's a nice limit, actually. It's a calculus issue because there's an R on the bottom. The limit is R approaches infinity. Okay. You know what? In fact, I think what I would say is this. A half mv initial squared plus mgh? No. K Q1 Q2 over R initial. That's going to equal K Q1 Q2 over R final. That doesn't look like a final, Mr. Dueck. Right now, I can't solve this because they didn't tell me the mass, so I would need to tell you the mass. Suppose I also said that the mass of this was, what? 1.2 times 10 to the negative 10 kilograms. What's this question asking me to find when it says how far until it stops? What's it asking me to find? I don't see a D in here anywhere. I think you thought it right, but I'm being fussy. Okay, final radius, final radius. It wants me to find RF. It wants me to find that. I could try and get RF by itself right now. It'd be yucky. I would instead probably evaluate this whole thing as a number. I would probably crunch this. In fact, I'm going to. I'm going to say this is 0.5. What did I say the mass was? 1.2 times 1.2 times 10 to the negative 10. 5.2 times 10 to the 7th. Plus, Carly, what mistake have I made? Oh, okay. 9 times 10 to the 9th. Let it go, Mr. Dueck. Yeah, right. 8 times 10 to the negative 6. Am I going to put a negative or a positive in here for the second charge, too? I'm going to put it, it's a scalar. It does right now have negative energy. Why? Because out at infinity is when it has 0. We would have to do work to get it. It doesn't want to go out to infinity. It wants to fall towards. So I'm going to put the negative in. All over 2. That equals K Q1 Q2 over R final. I would now evaluate this. I'll do it really, really quickly. 0.5 times 1.2 negative 10 times 5.2, not negative, 7 squared, plus, now I've made up these numbers and I have no idea. We may end up with an answer that's impossible. I may have inadvertently given this thing too much information, too much energy. Let me double check. A half mv squared plus 9 times 10 to the 9th, 8 microcoulombs. It is 6, right, Mr. Dueck? Yep. Divided by 2. Oh, okay. Wow, yeesh. We may end up with a really, really big radius, like in the trillions or something. This is what happens when I make these up. Anyways, I get 162,239. 162,240 equals K Q1 Q2 over R final. Now, how would I get R final by itself? That's going to end, come on. That's going to end up there. That's going to end up there. For what it's worth, this is going to be bad. 9 times 10. Yeah, I'm getting a negative radius when I put the negative charge in, so I've made up bad numbers. Okay. I made up yucky numbers. I didn't have it going faster than light, though, did I? No. Because the speed of light is 3 times 10 to the 8th. Why am I getting... I'll have to run around with it. But that would be something else I could do with 2 points. Or, Rachel, I could start out... I could make these both positive. Start out at infinity with a certain speed and ask when it comes to a stop, because it would be repelled. Okay? What else can I do? In fact, I think I have this in a diagram, Mr. Dueck, don't I? Sure. Same picture. How much work to move the negative charge to location P? So here'd be another question I could ask. How much work to move that negative charge? Does it want to go to location P? Which way would that negative charge prefer to fall? Left, towards. So it is going to take work. How much what? Work. Can I go force times distance? Changing force. So this time it's going to be Do you see any speeds in the question that suggest that this charge will be moving beforehand or moving afterwards? No, then I can say that. It's going to be, now there was 2 ways to do this. If I had calculated the potential difference between here and here, I could use QV. Since I haven't done that, I'm going to have to fall back on final minus initial. It's going to be K Q1 Q2 over R final, which is 4, not 2, minus K Q1 Q2 over R initial, which is 2. You would put negatives in here. So the 6 would be a negative 6 times 10 to the negative 6 microcoulombs. Do you want me to go further, or are you guys okay actually typing the numbers in and being able to get that? What else can I ask with 2-point charges? I've done the potential energy question. I've done work. I've done electric field. I've done potential voltage. I didn't exactly do potential energy, but we had to do potential energy to do these last 2 questions, so it cropped up. I think that's about it. Yeah. How do you find like time or acceleration? Okay? So, first of all, I can't, because the force is changing, F equals what times what? The basic definition. F equals force times distance. F equals what times what? The basic definition. F equals what? MA. For all these charges, Darian, is the mass changing? But the force is changing? For all these, you don't have a constant acceleration for point charges. So first of all, I would have to ask for, if I did ask for acceleration, because it's getting bigger and smaller, okay? Probably, okay? Or use the Unit 1 kinematics stuff. Can you find a specific question where I asked that? And I'll go over that if you can, okay? I have no problem asking for time or acceleration between plates. So if you're asking me a question and it's between plates, that's totally different. But if it's 2-point charges like this, okay, that's coming down. That's much easier. So you know what? I'm going to go gone. And in fact, I'm going to use it as my segue. What can I ask for parallel plates? See if I can find a nice picture of that. Sure. Here's a lovely picture. Looking desperately for something that had no charge or numbers on it. So, what could I ask you? First thing I could ask is if Q equals -3 electrons, how much work to move it from the top to the bottom of the plates? Okay. By the way, electron will be attracted to the positive part. Which part is positive, top or bottom? So if you start at the top, it would take work to move it down because it wants to fall up. Okay. What did I ask you to find here? Work. Work is going to be yep. Why is the bottom positive? The bottom is not positive. No, it wants to fall up. So which is positive, top or bottom? Top. Did somebody say bottom and I just went? Oh. Well. Do you guys actually even hear it when Grant moves his voice anymore? Because you know what? I don't even notice it, right? How many of you have ever been in a rainstorm where all of a sudden you're inside and all of a sudden the rain really picks up and you can hear it just pounding, and then after about 30 seconds you don't even notice it anymore? Right? It's amazing what your brain can just tune out. Okay? So Darian, can I go back? At the top is positive, bottom's negative. An electron would want to move up, so you'd have to lift it down. And I know that sounds strange saying lift it down, but in this diagram, you would have to do work to move it to the bottom. Is that okay? How much work? We're going to assume we start and end at rest. Here, the easiest potential energy change in potential is Q change in voltage. Q change in voltage. What's the charge? 3 electrons. What's the voltage? 600. Okay. It's going to be 1.3 times 1.6 times 10 to the negative 19. Mr. Dueck, you're doing work. You should put a negative in. Well, first of all, I know it's going to take a positive amount of energy. Technically, by the way, what's change in anything? What's the change in voltage? What's my final? Where am I ending up? 0. What's my initial? So really it should be, and I could still put the negative in there. I just know I want a positive answer because it is going to take work. It does not want to move that way. So I got really sloppy there, but it is a negative and it is a negative. Okay? Whatever the heck that is. Well, crunch the numbers, Mr. Dueck. 3 times negative 1.6 times 10 to negative 19 times negative 600. It would take that many joules of work. Not a very big amount. Okay? What else could I ask? Same picture. Okay? You had said, what about speed and things like that? So certainly I could say if the charge has a mass, well, heck, if the charge is an electron, find its speed when it hits the top plate. Let's assume we start and end at rest. What does this question want me to find? Speed. Just more basic. What does this question want me to find? More basic. Speed. Did it say velocity? Speed suggests a scalar. Did it say work? This has a change in height. This has a change in speed. You know what that's a job for? Conservation of energy. KE initial plus PE initial equals KE final plus PE final. Starting at rest, and you're hitting the ground, you're using up all of your potential energy. This is the equation that had the V and the V in it. QV equals a half mv squared. V equals 2qv over m square root. Okay? Are we inside a square root? I want a positive inside the square root. Yeah, I know the charge is negative, but again, there's a voltage. Anyways, just put positives in here. Okay? I'm going to assume you could crunch this yourself, but now I can start to answer some of your question because, Darian, you asked, right? This was your question? Yeah. Okay. Now I have a constant force, so I can say find the acceleration because F equals ma. Hey, the mass ain't changing, the force ain't changing, so the acceleration ain't changing. How could I do this? Well, did they give me the distance between the plates? 4.2 times 10 to the negative 2, 0.042 is really what that's saying. Could you find A? VF squared equals A equals VF squared minus VI squared all over 2D. Could you find time? Yeah. I would probably find A first, and then you can use T equals VF minus VI all over A. Could I find force? Sure. Now that you know A, you could go F equals MA, or you could go F equals QE, which is Q voltage over distance. Should get the same answer for both. Okay. Is that all right? What else can I ask with plates? I could give you an initial speed. I think I have a picture of one somewhere here. So here's kind of a cool one, number 13. This is from a different review, but I think there's one very similar or maybe even identical in your review. This one says the proton will be stopped momentarily in what region? Okay. So now we have this proton moving already. Did they tell me the proton's initial speed? Say no. What did they tell me? Its initial, careful. Kinetic energy. What do they want me to find? This proton, when it will be stopped. You know what? I still think this is falling. Only you'll notice we're getting more and more and more and more positive as we move to the right. This proton is going to feel a force slowing it down. There's going to come a spot where it actually stops and gets repelled. Because like, repel. You know what? This is a change in height and a change in speed. This is like throwing something up and watching it slow down, slow down, slow down, come to a stop. This is a job for conservation of energy. Conservation of energy. So I would say KE initial, PE initial equals KE final plus PE final. Right? This is initial. Final is somewhere in here. I don't know where. Initially, just like when you throw something up, what's your initial potential energy on the ground? 0. Oh, and it said stopped. Right? Now, potential energy between plates is QV. Now, normally I'd go a half mv squared for kinetic, but wait a minute. They told me it's just 2.1 times 10 to the negative 17. This is actually easier. I don't need to even go bother going a half mv squared. What do they want me to find? What voltage is required to bring it to a stop? I'm willing to bet, divide by Q. It's a proton. You'll find maybe like you get 180, then it'd be this region. Or if you get 310, then it would be this region here. Or if you get 216, it'll be this region here. You can tell when it's going to come to a stop. All based on what I can do with plates and conservation of energy. Is that okay? I don't know why I'm looking at you because you asked that earlier question, but it's all good. Maybe it's because I don't want to look at Anthony. Okay, anyways. What else can I ask? So point charges, I think I've done my rant. I have an answer.
Are you ever going to ask us to find the charge
The charge. You mean the voltage? Or do you mean the charge?
No, the charge. There's a question in the
What lesson, what number?
lesson 7, number 10.
Lesson 7, number 10? Telling me time to get home. Too many reminders on my computer. Okay, this is different because now we're taking mass into account. So now it's in equilibrium. This is actually pretty easy. I'll get you started on it. I don't think I asked it to you, but at the same time there's some good review here, so I'll do it anyhow. So the fact that it's at equilibrium says this. What are the forces acting on this charge? Get the obvious one. I have to include gravity, which is why they gave me a mass. Okay? For an electron and a proton, the masses, so this mass is 10 to the negative 10. Remember, an electron's mass is to the negative 31, and a proton's mass is to the negative 27, so small as to be negligible. Here, this is an oil droplet or something that has some mass. And I have electric force up. How do I know it's up? Because it says it's in equilibrium, otherwise it would be accelerating down. So I can say, what the heck is Fe? Q times the electric field. I don't know the electric field. Well, that's going to be Q change in voltage divided by distance equals mg. I have no problem with the left part. You can certainly expect me that I think it's fair game for me to say, find the force or find the electric field using QE. So either I'll give you the force and the Q and you can find the E, or I'll give you the Q and the electric field, find the force. And also clue in that would then allow you to either find how far apart the plates were or what the voltage of the plate was. That would be fair game. Okay? What else can I ask for plates here? Now I notice I wrote that. Find the final speed. Oh, make sure you're okay with electric field diagrams. So here's an electric field diagram. Remember, the lines tell you the direction of the force. First thing, are these two charges like or unlike, and how can you tell? Okay, which one? I heard someone say like. The good news is you're right. The bad news is you're also wrong. Sorry? Okay, you can see that there's some repelling going on here, so like repel. Are they the same size? Well, I noticed this one has fewer lines than this one. This would be a bigger charge. So magnitude different, sign different. The answer to this would be D. Now, if they'd given me some arrows, I could even tell you which one was positive, which one was negative. How? Because the arrows always point from positive to negative, because it always shows you which way a positive would want to move if it could. Sorry? I can't hear you. Ready? Count with me. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 lines? Oh, you mean the sign's the same? Yeah. You said like, did you not? Oh, did I say different and different? Sorry. Different and say C should be the answer. Yeah. Yeah, C. Way to pay attention. Glad you're paying attention. I know what I'm looking for, Mr. Dueck. Let me see if I can find one like this. Here. Okay. Something like this here, where it says how much work must be done to move a blah, blah, blah. So I'm going to steal this picture. How much work must be done to move a 5.0 micro... Do I have a little mu here somewhere, Mr. Dueck? I think I do. Insert a symbol. Hey, micro coulomb charge from X to Y. This question looks really terrifying, except let's make it a bit smaller so I can fit it all on one screen. But what's it asking me to find? Work. Work, scalar or vector? Scalar. This is all going to be scalar, 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 scalar. In fact, I think what I would do is I would find the voltage at location X. How? It's going to be KQ1 over R1, where this is Q1. But do you notice Q1 and R1 are the same as Q2 and R2? You could just go times by 2. That would give you the voltage there. Then I would repeat. I would find the voltage at location Y, which is going to be 2 times KQ1 over R1. You know what? Instead of calling it 1 and 1, let's call it Rx, and let's call it Ry. Then the work is just going to be the charge that you're moving times the change in voltage. We're changing anything as final minus initial. Do you want me to do that, or is that okay? We did one like that in the notes and in the homework. Now, I'm going from memory. I don't think I put one like that on the written. I may have put one like this on the multiple choice because I noticed in both of my tutorials from previous years, I seem to have mentioned that question. And I apologize, I didn't look at the tests this weekend. I was busy reinstalling all my software. And I photocopied the tests, I think, over Easter, so they're not in my brain immediately. Yeah?
Are you going to give us a hint on what the principle of physics?
Am I going to give you a hint on what the principle of physics question is? I can't remember what the principles of physics using... Oh, you know what? I just remembered it. I think it's one that you can completely crunch with numbers if you want. It's a before and after question. And I'll even be more specific. It's a before and after asking you which one's bigger, which one's smaller, kind of a dealio. Okay? You can do it algebraically. In fact, you can do it, if you're really clever, in about 3 lines. But you can also, there's actual data in the part B of the question, so you can actually say, oh, I can just crunch this whole thing, very similar to what I did for part A, with different numbers, and then just compare my answers. I think that's the using principles of physics, right, to explain question. I think. So, specific questions that you want me to go over from the review, or, yep. That I like, I will in a second. But first, specific questions that you want me to go over from the review or anything like that. Number 2. This one here? Okay. Never mind. So it wants the electric field. It's point charges, so I'm going to use K Q over R squared. Now Q is 92 protons, 92 of the 1.6 times 10 to... Oh, is that what is that it there? You didn't... Sorry, what was that, Kylie? Nothing? Squared. Okay. Oh, and direction. Well, from positive to negative. Let's see. Which way would a positive... You know what? Away from the nucleus, because the nucleus has a huge positive charge. Yep. Lesson 8, number 8. Did I assign number 8? Did I? I did? Okay. I just didn't last year, apparently. Darian, this is also asking a time question, but this is a bit different because this is from the cathode ray tube. Okay. So, really, to do this, I need to get a good picture of the cathode ray tube. So there's the cathode ray tube, and now let's get number 8, Mr. Dueck. Okay. So here's what it's saying. It wants to know how long it takes the electron to travel that distance there. It wants time. Okay. Horizontally, which means if I go, I can do that. The time is just going to be the distance divided by the velocity. Did they tell me how long the plates are in the question? Yeah, although it's not on my screen. 5 centimeters. So the time is going to be 0.05 divided by how fast? You know what? It's this velocity here. No, because then it won't go anywhere. Try dividing by 0, your calculator will barf at you. It's the velocity after I go through the accelerating plates. Now, Darian, this part is totally fair game. What was the velocity? That was when all of your potential turned into kinetic. It's this velocity here is what's going to go right there. So what's going to end up down here is going to be 2qv divided by the mass square rooted. That's the velocity there, and that'll give you the time to go that distance. That's from the cathode ray tube. Darian, I'm not giving you one where I'm asking you to find a distance to the right as you're traveling between plates. I'm pretty sure there is a question where I ask you to find either a speed or something, and then ask you to do something with the speed crossing the plates, going between, like up and down. Okay? Either find a VF or find an acceleration or find a net force or something like that. Well, no, find a VF, definitely, that is fair game. Once you find VF, either ask you to find a time or an acceleration or something like that. Is that okay? All right. What do I like? You know what? I need to pause. Excuse me. I like number 3. I like number 3. Number 3 is a nice question. And in all of these, I'm giving you either questions that I like, or that are very similar, or maybe they're going forwards and the test goes backwards. So whoever said is we're going to be on the test, maybe, or something similar. Number 6, I like number 6. I like number 6. Now, number 6, they gave you the voltage between the plates, but they did it by showing you the battery that we're hooked up to. So this isn't quite fair game yet in that I haven't done enough circuitry with you, but I like the idea of saying, oh, if I tell you the voltage and the distance, you should be expecting to find the magnitude of the electric field and direction. Maybe there's a better one. I love number 7. I love number 7. Number 7 is a lovely question. I like number 10, I like number 10, I like number 10. I love number 12, I love number 12, I love number 12. I love number 14, I love number 14, I love number 14. Oh, so here's one. I like number 16. I like number 16. This is also a speed question. Here, though, you have a changing force. You're still going to use conservation of energy, KE initial, PE initial, KE final, PE final. It's just your PEs are going to be KQ1, Q2 over R. So it'll work. It's doable. I like number 18. I like number 18. I like number 18. Mr. Dueck, that has vectors. No, what's it asking you to find? Voltage, scalar or vector? Don't you worry about the angles. They gave you the distances. That's all you need. I like number 19. I like number 19. I like number 19. I like number 20. I like number 20. I like number 20. There is going to be, on the multiple choice, something like number 21 where I give you some kind of an electric field picture. And I say, either tell me which one's positive, which one's negative, or something like that. I like 22, I like 22, I like 22. I like 23, I like 23, I like 23. .27 is fair game for multiple choice, but not for written, because here it's electric field with angles. These would be vectors that you would have to add tip to tail. I like 28, I like 28, I like 28. Thirty is good, 30 is good, I like number 30. I like number 33, I like number 33. I like number 35, I like number 30. By the way, if you haven't noticed, there's been like 6 or 7 where you're finding an electric field either between 2 point charges or in this case to the right of point charge, but finding electric field when there's 2 charges. I like 36, I like 36, I like 36. 37 is good, 37 is good. This is 3 charges, but they're in a nice straight line, so it's not hideous. I like 39, I like 39, I like 39. So, I talked about the cathode ray tube. I'm not going to be putting specifically any cathode ray questions on your test on this one. And the reason is, in real life, we don't deflect the electrons with plates. Well, we don't deflect them at all anymore with flat screen, shut up. But we moved to solenoids and magnets. We are going to revisit the cathode ray tube properly about middle of May. So all these CRT questions you don't need to worry about unless there's clearly plates and you're finding a speed. I like 47, I like 47, I like 47. There you go. Any other questions? Okay, let me pause.